Welcome to the lesson on tackling class imbalance, where we're going to discuss how to deal with highly imbalanced data sets. Class imbalance is a situation in which one of the classes in your data is much more common than the other ones. For example, let's say that you're doing a binary classification of your network activity logs, where you're looking at the activity in your network and classifying whether it's benign, normal activity of just ordinary users that you're expecting, and activity that is actually malicious, maybe a hacker or data exfiltration or something of the sort. So you have two classes, and in any ordinary circumstance, almost all of the logs are going to be benign. 99.9% of the data will be labeled as benign, and you have very little data representing the smaller class of malicious. The problem with these sorts of very imbalanced data sets is that they make it extremely difficult for a classifier to perform well. The classifier simply doesn't have enough data on the minor class to learn much. But the difficulty of class imbalance doesn't end there. You also have to make sure that you select your metrics very carefully. For instance, accuracy is a poor metric for imbalanced data. You see, if 99.9% of your logs are benign, then even a trivial classifier that predicts everything to be benign is going to get 99.9% accuracy. In other words, the accuracy is extremely high. The accuracy is great, but you're not actually catching any malicious activity, which is the whole point of the classifier. Fortunately, there is a number of techniques for helping deal with class imbalance. Techniques that we're going to cover are 1. Weighting. In weighting, you give each class a different weight so as to make one class's examples appear more important than another's. This way, if you have, for instance, a binary classifier whose data is 99.9% benign, you can make each instance of a malicious sample have a much higher importance by adding a higher weight corresponding to the sample in the classifier's loss function. Then the classifier will be much more likely to detect this malicious sample. The second technique is called upsampling, and here you take samples from the minor class and you basically just duplicate them. As a consequence, your classifier has more of an opportunity to learn about this minor class. However, there is a downside, which is overfitting. If your classifier sees the same sample over and over again, it might begin to start memorizing it in quotation marks. The third technique is called downsampling, where instead of upsampling the minor class, you're going to downsample the majority class. Here, the disadvantage is obviously that you're using less of your data, but at least you're able to balance it. And the final technique we're going to cover is specially crafted classifiers, which are classifiers that have been designed to perform class balancing techniques in their very nature. So you don't have to worry about the other techniques of balancing, sampling, upsampling, downsampling, weighing, because the classifier will take care of that for you. To see these techniques in action, I'm going to load some data, and I'm also going to import my libraries. And a new library we haven't seen before is scikit metrics, and in particular we're going to use the function balanced accuracy score so we can assess imbalanced data sets. So what we're going to do is test out all the techniques using balanced accuracy score. So first I'm just going to test out ordinary random forest without using any balancing techniques. So vanilla random forest gives us a score of 86.6%. Next, I'm going to use weights in my random forest classifier, and we'll see how that performs. The score is 96%, which is already a great improvement over the vanilla random forest. Now, let's try upsampling. So I'm going to take samples from the minor class, and I'm going to duplicate them using resampling. So once I do that and put my dataset back together, I'm going to run random forest, and I get a score of 99%, which is again an even larger improvement. Now let's try downsampling, taking only a proportion of my major class, and then I'm going to run random forest, and I get 98%, which is not as good as the upsampling, but definitely an improvement over the other two techniques. Finally, I'm going to try out a classifier that has been designed to work with imbalanced datasets. So I'm going to use the library called Imbalanced Learn, and I'm going to try out the balanced bagging classifier. And the score I get is 98%. 5%. So we see that every single one of our techniques did improve the balanced accuracy score. The winner in this case was upsampling, but you never know what's going to happen in your own data. Perhaps one of the other techniques will perform the best. Now that we are thoroughly skilled with dealing with imbalanced data sets, let's see how to solve another challenge that often arises in cybersecurity, namely dealing with a false positive constraint.